from the point group symmetries to molecular orbital theories, as well as to coordination complexes. So quite a lot of stuff we have covered in last few weeks. So the exam will be primarily focused on that aspect. Right? So I know that most of you must have reviewed the material that we were talking about. And today we are holding this special session to, make sure that if you have any questions unanswered or something that comes up while you're reviewing, it's natural that you might have understood when I was presenting the lecture, but then when you're reviewing yourself, oftentimes you see a situation where, oh, well, I don't think I really understand this. Okay, so this session is exclusively to make sure that we are all on the same page. If you feel that you're not understanding something, please tell yourself you're not alone. So let's talk about the first phase of the exam, that is the molecular orbital theory. Before I continue, I just want to let you know, remember last time you asked me how many questions will be there, 20 or 25? So we made 25 questions. Of which roughly about five to six questions maybe from molecular orbital theory. And then there'll be about another 8 to 9 questions on point group symmetries. The remaining will be in the coordination complexes, which involves naming the complexes, finding the isomerism of the complexes, and various types of isomers, and naming of the complexes, and also on the 18 electron rules that we talked about. Okay, so that's the broad distribution of the questions that you will be seeing in the exam. All right. Mostly there will be no numerical questions. These are all conceptual, as you can see. I don't think we have done too much math, right, in these topics, except to maybe to find the bond order, from the molecular orbital picture. Finding the number of bonding electrons, antibonding electrons, take the difference and divide by 2 to get the bond order. So that's the complex math, if you want to call that. Beyond that, I don't think we have any true issues in terms of math. Thanks, Alyssa. How are you? Good seeing you. So do we have any issues in the molecular orbital diagrams? As long as you understand the sequence, the way the molecular orbitals are arranged. As you know, it will be mostly concerning the homonuclear diatomic molecules. Okay. So having the same atom on both sides of the bond, like N2, H2, F2, N2, B2, Li2, C2. These are all homonuclear diatomic molecules. You should know which ones make sigma bonds, which ones make pi bonds, what are the conditions for the atomic orbitals to combine to form the molecular orbitals. In other words, the conditions for the linear combination of atomic orbitals. That you should make sure that the energies are similar and the symmetries are proper. But you cannot have a molecular orbital from an s orbital and a px orbital, assuming that the z-axis is the bonding direction. You can have an s and pz, but not px and py. I mean, these are all the concepts we went over in construction of the molecular orbitals, and we expect you to know those things. Finding the unpaired electrons, like how many unpaired electrons given any molecular electron configuration, right? If we ask you how many unpaired electrons will be there. Or sometimes we'll ask you what happens to the bond order if I remove an electron or add an electron. In what way would that alter the bonding characteristics? Does it improve the bonding or does it cut down the bonding? So basically, you're counting again the bond order, or basically, if you're removing electrons from bonding orbitals, you weaken the bonding. On the other hand, if you are adding electrons to the bonding orbitals, you improve the bonding. Similarly, if you remove electrons from anti-bonding, you're improving the bonding characteristics. If you are adding electrons to the anti-bonding level, you will weaken the bond. I mean, those are all the things we went over, but just a quick review of what we did. Are there any issues, any questions? In the next part, I think we talked about the symmetry operations, symmetry elements, the rotational axis of symmetry, the plane of reflection, the inversion centers, and the improper axis of rotation, as well as identity, right? That is doing nothing. So we have taken lots of examples in terms of identifying highest fold rotational axis of symmetries in molecules. We're given plenty of molecules. Then plane of reflection. For example, if you have an ideal tetrahedral molecule such as methane, we have 6 planes of reflection in it, and we've talked about all the reflection planes. We talked about 3 different types of reflection planes, right? The vertical plane of symmetry, the horizontal plane of symmetry, and the dihedral plane of symmetry. All 3 of them, we have given you examples of which is a sigma D, which is a sigma V. And in all the cases, if you go back to my notes, I have given the definition. When would you call a plane a sigma H, right? We talked about the conditions. And how many sigma H you can have in a molecule? 1, 2, 3, only 1, right? Because any plane that is perpendicular to the highest fold rotational axis of symmetry, if that plane exists, that should be designated as horizontal plane of reflection, sigma H. And then we talked about sigma V's that contain the highest fold rotational axis of symmetry. So does the sigma D too. But the difference there is if a plane contains most number of atoms and still contains the highest fold rotational axis of symmetry, that is sigma V. And if there is a plane that contains least number of atoms, but still contains the highest fold rotational axis of symmetry, then that should be designated as sigma D. We've given you examples of sigma V's and sigma D's in molecules. So given any molecule in the exam, you should be able to identify how many sigma H, how many sigma V, how many sigma D the molecule may have. And then I also gave you a lot of examples of the improper axis of rotation. That is sometimes known as rotoreflectory axis. So that means if a molecule upon rotation and reflection in a plane perpendicular to the axis of rotation, if that molecule, if that operation, in other words, the combination of operations, bring the molecules to the shape that was before or indistinguishable form, then we say that it's an improper axis of rotation. We gave you several examples of improper axis of rotation, starting with methane to allene and several examples. Finally, the last part of the exercise, what we have done is we have looked at all these symmetry operations in molecules, and based on the presence or absence of some of the symmetry operations, we were able to classify molecules into various point groups, right? And I gave you a chart, and I also gave you the liberty of choosing anything that you are comfortable with, because all these charts will give you more or less the same answer. Okay. That makes sense. I think that's what we did, right? We took a lot of examples. We never repeated a single example, but we kind of took diverse set of examples and tried to classify as many molecules as possible into various point groups. And we noted the similarities and the differences when the molecules belong to different point groups, right? So, and then we moved on to coordination complexes. We basically gave you a history of these complexes, and then we
I had a real quick question.
Yes, sir.
For the symmetry, can you give an example of the difference between like a D3H molecule and a D3D?
Just give me some examples. Let me first talk about a molecule such as PCl5, right? This one has a C3, right? The axial Cl, PCl. These three chlorines are in the plane, separated by 120 degrees. So that Cl, PCl, that line there, forms the C3 axis, right? And then you have a plane that is perpendicular to this one. Right? That is a reflection plane because you have a chlorine on the top, chlorine below, and upon a reflection, these two chlorines exchange their positions and the resulting structure looks indistinguishable from the previous one. So we have a sigma H here. And we also have three C2s because each of these PCl bonds in the plane serves as a C2 axis. So if you go the decision tree, this now becomes as a D3H molecule, right? So the difference between a D3H and a D3D is in a D3D molecules, we do not have a sigma H. Okay, so let's take a simple example of a D3D molecule. Okay, is this clear to you why this is D3H, right? Austin?
You said it was D3H because it has a sigma H?
Yes.
Okay.
It's a
And
sigma H, yeah.
The sigma H has a C3?
The sigma H is perpendicular to the C3.
Oh, it's perpendicular, okay.
That sigma H is the plane that contains the equatorial chlorine atoms in the phosphorus. You know, this is a trigonal bipyramidal geometry, right? So we have both axial and equatorial chlorines. We have three equatorials and two axial chlorines. So if you look at the phosphorus and the three equatorial chlorines, that plane that contains these four atoms is your sigma H.
Okay, thank you.
Okay. On the other hand, let's say if you change this to a fluorine, then you lose the sigma H. Does it make sense? It still has C3, but it does not have sigma H. So this basically works out to be a C3H type of a molecule. But let's talk about C3, a D3D molecule, okay? And let's see how the molecules are different. That was your question. So let me take now an example of a D3D molecule. So that is C2H6 in a staggered form. I think we went over this example in the class, right? We took this example to illustrate the presence of the S6, right? So let's talk about this molecule. If you look at this, that is that's your hydrogens here, C2H6. Now, does it have a sigma H?
No.
It does not have. Now this one, if you go through the point group classification chart, you will see it's a D3D molecule, not D3H, because it does not have a sigma H. So I gave you two examples, one for D3H and one for D3D. Does that make sense, Austin?
Yeah, so then the D3D has no sigma H.
No.
What's the difference?
Yes.
Okay. Thanks.
Sure. Thank you for asking these questions. It's very important. So this gives us an opportunity to go back and look at both examples. Other ones. Anything else on that topic? Anything that's not making sense? So in the coordination complexes, again, you have to be familiar with the naming of the complexes, which goes where, and how to find the oxidation states of the metals, whether the complex is negatively charged or neutral or positively charged. So we have a different naming scheme for complex ions, which are either neutral or positively charged, and one for those that are negatively charged complexes. So all negatively charged complexes will have a suffix of ATE added to the name of the metal in its Greek name, right? Followed by the oxidation states. And the ligands are named alphabetically, and keep in mind the anionic ligands are named first, followed by neutral ligands. So that's a summary of all that we've been talking about in terms of naming of the complexes. And sometimes when I give you a name of a complex, you should be able to identify the formula of the compound too. So it goes both ways. So I need to practice those two. And we also have to understand that if the name of the ligand contains a numbering information, then we can't use di-tri, but we have to use words like bis, tris, tetrakis. So you should know when to use di, tri, tetra, and when to use bis, tris, tetrakis, pentakis, hexakis. It depends on the name of the ligand. If the name of the ligand is simple, like fluorine or chlorine, you don't need to use bis and tris. But if you have ligands that have a naming information like ethylene diamine or tetraphenylphosphine, if you have some numbering information, then if they serve as ligands, and if there are multiple ligands of those, then you have to use bis, tris, and tetrakis. And then we have to identify different types of isomers. We have talked about hydrate isomers, linkage isomers, ionization isomerism, stereoisomerism, cis-trans isomerism, Fachner isomerism, right? And then we also talked about optical isomerism. Quite a lot of stuff we have done if you go back. So you should be able to identify that. The good part of it is because we're taking the exam online, we are free to open the books or take the notes. Keep everything ready next to you, just in case you need to refer to it. In an in-person exam, unfortunately, that's going to be even more difficult because you will not be allowed to open any book or notes. Our university administration is strongly against proctoring anyone taking an online exam. And we are good with that because you're all honorable students and you take your education and assessment seriously. And we trust each and every one of you. So we are okay with the administration's administrative decision not to impose online proctoring. So it kind of removes some stress out of you. And you have plenty of time to do those things. So after this exam, we will have a final on the day you must have received a time, right, for the finals. The final will be cumulative, so that will contain material from exams 1 and 2, and also the materials that we are going to discuss in the time that is remaining in the semester. which most likely include medicinal inorganic chemistry for those of you who are biochem majors, acid-base chemistry, and descriptive chemistry of elements. So that will be the total content of the inorganic chemistry course, as per the syllabus that I have given you, of course. Other questions? Anything that requires a revision or something that needs to be done one more time? So how many of you feel that you're learning something in this course? Oh, great, everybody, almost, yeah. This is something you have not heard before, right, in other chemistry classes? These coordination complexes, point group symmetries, molecular orbital, most of you must not have seen in other classes. Is that true, or is my assumption wrong?
Professor Chari,
Yeah.
someone did ask a question in the chat.
Oh, okay, I'm sorry.
No, you're good. It was just now. I just wanted you to see it.
Let me see, chart box. Let me see. Oh. Okay, great. That's thank you. I don't get that notification when I see a chart here. Okay, let me go over this. All right. CH3CO. Okay. Now, because there are no counter ions here, we can assume that this is a neutral complex. Now, if you look at the ligands here, I have a metal ligand. I have 4 carbonyl ligands, correct? So carbonyls are neutral ligands, and methyl is a negatively charged ligand. CH3 is a -1. So what should be the charge on cobalt then? It should be +1. So that answers the first part of the question. What is the oxidation state of the metal in this particular example? So we say it is cobalt +1. The next question is, how many electrons does this have? All right. So methyl is an anionic 2-electron donor. So that gives 2 electrons, plus there are 4 carbonyls. Carbonyl is a neutral 2-electron donating ligand. So that makes it 4 times 2. So this is about 10 electrons here. And how many electrons are in cobalt 1+? So to answer that question, we need to know what is the electronic configuration of cobalt metal, right? Cobalt is argon, right? 3d7 4s1, 3d7 4s2, sorry. There are 9 electrons in the neutral cobalt, but here I have a cobalt in +1 state. So if you look at the 9 valence electrons of the neutral cobalt, and if you remove one of the electrons, there will be a total of 8 electrons in the cobalt, so the total will be 18 electrons. So the total electron count of this particular complex so this is methyl tetracarbonyl cobalt 1 complex. You see the way I'm calling this complex, I'm also naming it. Methyl tetracarbonyl cobalt 1 complex is an 18 electron complex. That's a stable complex. Remember we talked about stability comes when you have 18 electrons to it.
You said the carbonyl has 10 electrons?
No, carbonyl is only 2 electrons. So 4 times 2 is 8, and methyl has 2 electrons. 8 plus 2 is 10.
Okay, thank you.
Make sense? So the beauty of it is the way we have learned this topic is no matter what the complex is, we should be able to break it down and be able to answer the question. Thank you, Mike, for asking this question. Mike, are you okay with this question, with this answer? Are you there, Mike? Michael Wolde. Can you hear me, sir? Oh, too bad. You asked me a question and then leave. Okay, other questions? Okay. I got an answer, so he's happy with it. Okay, if I don't want to waste your time on this because we're repeating what we have been talking about all the time, but this session is exclusively for reviewing any material that was not clear during the original presentation and take any additional questions you may have. Okay, so if there are no further questions, I wish you all good luck with your exam. Do well, and just like your exam one, I was very proud of most of you have done great job, and I expect you to repeat the same performance moving to the second exam and also the final exam. I want all of you to succeed in this class. Okay. So two things, I want you to do well in the exams and also learn a lot of material. So these are the two aspects of this course, okay? So if there are no further questions, I see you all. There will be no meeting on Wednesday because Wednesday this time is exam time. So by Thursday or Friday, you should have the scores. And next week, next Wednesday, we'll start again with a new topic, medicinal inorganic chemistry and acid-base chemistries. All right. So see you all again next week.
I had a real quick question.
Yes.
In terms of like the exam, you said you'll post it Wednesday at 11 and then we'll have 24 hours?
No, I think it will be available from Tuesday onwards. Don't you see that in the canvas when it is available?
Okay.
Yeah.
So you'll post it Tuesday and we'll have how long to do it?
I think it's 120 minutes, I believe, 2 hours.
And it will be due by Thursday or Wednesday?
Wednesday.
Okay.
Wednesday evening, yeah. So you'll have 2 days time to finish. But once you begin the exam, you have to finish that in 2 hours time period.
Okay.
I don't care when you start, but when you start, you can't, start and then come back and then do this again over a period of 2 days.
Okay, thank you.
So you should finish it in one sitting. All right. So if there are no other questions, we see you all next week.
Thank you. Have a good day, Professor.
Thank you,
Good luck.
Chari. Have a good day.
Good day. You too. Okay. Thank you for coming to the review session. Bye.